Fluorescence requires a source of excitation energy. There are several main types of light sources that are used to excite fluorescent dyes. This tutorial introduces the types of commonly used excitation sources and presents some of the ways that filters can be used to optimize your experimental results. The most popular sources used for exciting fluorescent dyes are broadband sources, such as the mercury arc and tungsten halogen lamps. These produce white light that has peaks of varying intensity across the spectrum. In contrast, laser excitation sources, which will be described later, offer one or a few well-defined peaks, allowing more selective illumination of your sample. More recently, high-output light-emitting diodes, or LEDs, have gained popularity due to their selective wavelengths, low cost, low energy consumption, and long lifetime. When using broadband white light sources, it is necessary to filter the desired wavelengths needed for excitation. This is most often done using optical filters. Optical filters can range from simple colored glass to highly engineered interference filters that selectively allow light of certain wavelengths to pass while blocking out undesirable wavelengths. For selective excitation, a filter that transmits a narrow range of wavelengths is typically used. Such a filter is called a bandpass excitation filter. The high intensities and selective wavelengths of lasers make them convenient excitation sources for many dyes. The best performance is achieved when the dye's peak excitation wavelength is close to the wavelength of the laser. Compact violet 405 nanometer lasers are replacing expensive UV lasers for most biological work. The most commonly used lasers are the 488 nanometer blue-green argon laser, 543 nanometer helium neon green laser, and 633 nanometer helium neon red laser. Mixed gas lasers, such as the krypton argon laser, can output multiple laser lines and therefore may still require optical filters to achieve selective excitation. While a given dye's excitation maximum may not exactly match the laser's peak wavelength, the high power of the laser can still produce significant fluorescence from the dye when exciting at a suboptimal wavelength. Filters are important for selecting excitation wavelengths. They are also important for isolating the fluorescence emission emanating from the dye of interest. Detecting the fluorescence emission of a sample is complicated by the presence of stray light arising from sources other than the emitting fluorophore, for example, from the excitation source. This stray light must be kept from reaching the light-sensitive detector in order to ensure that what the instrument sees is due only to the fluorescence of the sample itself. When a single dye is used, a filter that blocks out the excitation light to reduce background noise but transmits everything else is often a good choice to maximize the signal collected. Such a filter is called a long-pass emission filter. If multiple dyes are used in the sample, a bandpass emission filter can be used to isolate the emission from each dye. Careful filter selection helps to ensure that the detector registers only the light you are interested in, the fluorescence emitted from the sample. LEDs are relatively new light sources for fluorescence excitation. Single-color LEDs are ideal for low-cost instrumentation where they can be combined with simple long-pass filters that block the LED excitation and allow the transmission of the dye signal. There are many options for light sources for fluorescence. Selecting the appropriate light source and filters for both excitation and emission can increase the sensitivity of signal detection to an astounding degree, making fluorescence labeling one of the most sensitive detection technologies available.